This is our continuing series on lectures on transport in one dimension, unidirectional transport, where we were looking at transport in a curvilinear coordinate system. Okay. If you recall, we had written down balance laws for a cylindrical coordinate system. This is useful when we are considering transfer in a pipe, for example, or an annular region. These are quite often used in practical applications, and in these cases, rather than defining a rather complicated expression for the boundaries in a Cartesian coordinate system, in this particular case, if we take x and y coordinates in the plane, the boundary would be defined by x square plus y square is equal to r square. We could solve the differential equations, of course, but then applying the boundary conditions on a complicated boundary becomes a problem. It is much preferable to have the boundary as a surface of constant coordinate. Therefore, we had chosen a curvilinear coordinate system, a cylindrical coordinate system, where we have two coordinates. One is the radial coordinate, which is the distance from the axis of the cylinder, and the other is the axial coordinate, which is the distance along the axis of the cylinder. In this particular case, we had first considered only variations in the radial coordinate, and we had derived a balance equations, okay, by doing a shell balance, where the rate of change of energy was equal to energy in minus energy out plus any sources. Energies in and out were products of the flux times the surface area. In the Cartesian coordinate system earlier, the surface area was a constant, so only the flux was changing. In this cylindrical coordinate system, both the flux and the surface area change with position. And for that reason, the differential operator, which represents the diffusion, okay, in this particular case is slightly more complicated. It is no longer just a second derivative with respect to the spatial coordinate. It has a slightly more complicated structure to it. We had solved the heat transfer across the wall of a pipe, a steady problem, and we had got this logarithmic profile for the temperature field, which is different from the linear profile you would expect if you had for transport across flat surfaces. Okay. And because of that, we had the logarithmic average radius entering into the definition of the area of cross section across which the transport takes place. Strictly speaking, the flux should be given just by this, but in correlations it is expressed in terms of the thickness times an average area, and that logarithmic average is given by this one. Okay. So, that we had seen in the previous lecture. And then we were doing an unsteady problem, where initially we had a cylinder of temperature T naught, which was immersed in a fluid of temperature T1, and we wanted to know how the temperature varies with time. As I said, this is a problem of practical importance. Okay. You very often in industries, either you have metal cylinders which we want to cool in water, or you have cylinders such as cans of different materials which are immersed in water in order to cool them, and one would like to know the rate at which the temperature decreases with time, okay, or increases to the outside temperature. So, the balance equation, if you recall, had the same form that I had earlier. The time derivative of the temperature is equal to the thermal diffusivity times this 1 by r d by dr of r times dt by dr. The boundary conditions, in this particular case I had only one physical boundary. That physical boundary was at r is equal to capital R. Okay, there was only one physical boundary where the temperature was specified. However, the radial coordinate goes from r is equal to 0 to r is equal to capital R. So, therefore, the interval for the radial coordinate r is from 0 to capital R. Of course, the radial coordinate is a distance, so it can go in any direction. Okay. We had assumed that there is no variation of the temperature with respect to the angle around the axis. We will come back to cases where we have to consider variations, but in this case there was no variation with respect to angle around the axis. So, in this case the interval for r is from 0 to capital R. That means that there is a boundary at r is equal to 0 imposed by the coordinate system itself, okay, because we have taken the origin at r is equal to 0. So, the interval is from r is equal to 0 to capital R, and at r is equal to 0 there is no physical boundary. However, there is a symmetry condition, as I had explained to you. Okay. It is only if the slope of this temperature curve at r is equal to 0 is equal to 0 that the temperature will be continuous if you take it from the right side or from the left side. Okay. The derivative has to be 0, otherwise you will have a difference in the derivative from the right to the left side. That means that the derivative cannot be uniquely defined at r is equal to 0. So, as long as there is no physical boundary at r is equal to 0, the boundary condition has to come out of symmetry, and that symmetry condition, as I had showed you, was equal to that the temperature derivative was equal to 0 at r is equal to 0. So, we had defined r star is equal to r by r. That was the scaled radius, okay. And defined in terms of r star, we find that at r star is equal to 1, okay, T is equal to T1, the temperature that is imposed on this outer boundary, okay, T is equal to T1, okay. And at r star is equal to 0, right, dt by dr was equal to 0. Okay. So, that was the temperature. I should actually use a partial derivative here, okay, because the temperature is a function of both time and position. Okay. And at t is equal to 0 for all r, the temperature was equal to T naught. That was the initial temperature of this cylinder. Okay. So, how does one scale the temperature scale? Okay, I had gone through that in the previous lecture. What is it that you would expect the temperature to be in the limit of long time? Okay. As t goes to infinity, the temperature of the cylinder should be uniform. It should be equal to T1, because that is the surface temperature. So, in the long time limit, the temperature of the entire cylinder should be equal to T1. So, it is preferable to define a departure from that T1 as the scale temperature, okay, the departure from the temperature T1 as the scale temperature. Therefore, we had defined T star is equal to T minus T1 by T naught minus T1. Okay. So, this is equal to 0 in the long time limit at all r, because the temperature everywhere would have equilibrated to T1. Okay. So, that means that at r star is equal to 1, the scale temperature T star is equal to 0, and at r star is equal to 0, partial T star by partial r star is equal to 0. Okay. At t is equal to 0 for all r, the temperature is equal to T naught, which means that T star is equal to 1. Okay. If I have defined my scale temperature, okay, as T star is equal to T minus T1 by T naught minus T1. So, those are the equations and the boundary conditions. Okay. So, my differential equation partial T by partial T is equal to alpha 1 by r okay, at r is equal to r, t is equal to T1, r is equal to 0, partial T by partial r is equal to 0. Okay. And at t is equal to 0, t is equal to T naught for r less than r. We have defined the scaled variables r star is equal to r by r and t star is equal to t minus t 1 by. Okay. So, that this became at r star is equal to 1, t star is equal to 0, okay. R star is equal to 0, partial t by partial r is equal to 0. Okay. Once I scaled it this way, you can easily verify that the equation becomes of the form partial t by partial t is equal to alpha by r square the equation is linear in t and therefore, it is equidimensional. Therefore, I can just straight away convert t to t star and I have two derivatives with respect to r and therefore, I will get a 1 over r square. We have not yet scaled the time and this equation makes it clear what the time scaling should be, because if I scale it by this factor, then the equation becomes dimensionless. Okay. So, therefore, I can define a time scale as t is equal t star is equal to t times alpha by r square. Okay. Once again, r square by alpha is a diffusion time, the time it takes for energy to diffuse over a distance capital R. So, that is the natural time scale by which to scale this problem. Okay. And if I use that natural time scale, I will get written in this way. This equation is independent of the temperatures, the thermal diffusivities and so on. Okay. So, it becomes a universal equation. Any problem that I had can be transformed into this just by scaling, regardless of what the material diffusivities and so on are. Okay. And scaled this way, the initial condition becomes that at t star is equal to 0, okay, t star is equal to 1, okay, for r star less than 1. Okay. So, therefore, I have the forcing in the initial conditions, okay, and the two boundary conditions that I have here for this problem are both homogeneous. They say that the temperature is equal to 0 or the temperature derivative is equal to 0. Okay. So, therefore, this becomes an eigenvalue problem which can be solved using separation of variables. Okay. So, back to the separation of variables procedure. Okay. T of r t can be written as the product some function of t times some function of r. Okay. Insert that into the balance equation. Okay. What you get is that r of r star times partial f by partial t is equal to f of t star times 1 by r So, separately write this function as a function of r times a function of t, insert that into the balance equation and then divide throughout times by r times f. Okay. Divide both sides of the equations by r times f. Okay. So, you will get 1 by f divide throughout by r times f. Okay. Now, in this equation, the left side is only a function of time, the right side is only a function of position. Okay. So, that means that both of these, the left and the right sides, individually have to be equal to constants. If that were not so, then I could change the location while keeping the time a constant and this equality will no longer be valid. Okay. So, the only way that this equality will be valid is if both of these, the left and the right, are both equal to constants. Should the constant be positive or negative? Okay. We had already looked at that when we did the heat transfer in a finite domain. If the constant is positive, the left side, if you solve it, it gives you a function that is exponentially increasing in time. So, it never satisfies the condition that as t goes to infinity, this t star should be equal to 0. Okay. So, therefore, the only way that you will get a solution that is decreasing to 0 as time goes to infinity is if the left side and the right side are both equal to negative constants. Okay. So, has got to be equal to a negative constant. I will call that as beta square, okay, where beta is any number. Okay. So, this has to be equal to a negative constant. Okay. With boundary conditions, okay, r is equal to 0 at r star is equal to 1 and partial r by partial r star is equal to 0 at r star is equal to 0. Okay. Those just come out of these boundary conditions. Okay. These are two homogeneous boundary conditions. Okay. So, therefore, for the radial variation I have to solve this equation. Okay. I can expand this out. Okay. What I will get is d square r by dr star square plus I am sorry, I made a mistake here, kindly note. I should have a 1 over r. Okay. That 1 over r comes out of this term here. Okay. I should have a 1 over r there. Okay. And therefore, if I multiply both the left hand right sides by r, what I will get is so that is the equation that you will get. Okay. Expand it out, the derivative, you will get d square r by d r star square plus 1 over r star okay. So, that is the differential equation that has to be solved. So, let me write it again. The equation becomes of the form d square r by d r star square plus 1 over r star okay, subject to the boundary conditions r is equal to 0 at r star is equal to 1 and okay, okay. I can rewrite this equation by multiplying throughout by r square and I will get r square partial square r Now, if I change variables, okay, if I change variables into beta, okay, okay, or r star is equal to x by beta. Okay. And doing a change of variables, r star is equal to x by beta, or beta is equal to beta times r star is equal to x. Okay. When I change variables, you will see that these two terms have 0 net dimension in r. Okay. It is r squared times the second derivative, r times the first derivative. Okay. So, the net dimension in r of these first two terms is equal to 0, which means that if I scale r by any coordinate, these two terms do not actually change. Okay. And I get equation of the form x square d square r by dx square plus x square r is equal to 0. Okay. Now, this equation has to be solved in order to find out what is this function r. Okay. It turns out that there is no analytical solution for this equation. Okay. The solution for this equation is what is called a Bessel function. Okay. The Bessel equation is of the form x square d square y by dx square plus x plus x square minus n square y is equal to 0. Okay. And for that, the solution is of the form y is equal to a j n of x plus b y n of x. Okay. These j and y are what are called the Bessel functions, and this equation is called the Bessel equation. This equation is called the Bessel equation, and j and y are called the Bessel functions. These equations are solved, they are tabulated. Okay. You find them in standard tables. Okay. These are similar to, in the case of a finite channel, we got sine and cos functions. Okay. Sine and cos functions, of course, they are also special functions. We can plot them. Okay. We know what the values are at different values of x, okay, for the sine and cos functions. Similarly, in this case as well, these solutions can be plotted. Okay. We know what their values are for different values of x and y. Okay. And using these, we can construct solutions. So, instead of sine and cos functions in the case of a finite channel, these Bessel functions form the basis set, okay, for this in an infinite channel. Okay. So, you can see that this equation corresponds to the Bessel equation with n is equal to 0. Okay. It corresponds to the Bessel equation with n is equal to 0. Okay. That means that the solutions are the solutions for the Bessel equation with n is equal to 0. Okay. So, the solutions are solutions in the form of Bessel functions. R is equal to a times j 0, okay, of x. X is beta times r star plus b times y 0 of x, where x is equal to beta times r star. Okay. So, these are the Bessel function solutions for the radial for the function r, which is a function of r star. Okay. And of course, these solutions can be plotted. Okay. For example, as a function of x, function of x, if I plot j 0 and y 0, okay. J 0 actually has a 0 slope and then it goes through 0. Okay. It oscillates. Okay. The amplitude of the oscillation decreases and the distance between zeros also decreases as x increases. Okay. This is the equivalent of the sine solution that we had. The sine solution as well oscillated, but it had a constant amplitude. In the cylindrical coordinate system, this is the equivalent of that sine solution. Okay. The other one goes to minus infinity, okay, and once again it oscillates. Okay. This is y 0, and this is J0. Okay. Boundary conditions, we require that the slope is 0 at the origin. Okay. We require that the slope of the temperature profile has to be 0 at the origin. J0 does satisfy that condition, Y0 does not. Okay. So, therefore, this constant B has to be set equal to 0, okay, because that solution does not satisfy the boundary condition, okay, that at R star is equal to 0, dr by dr star is equal to 0. Okay. This would imply that B is equal to 0. Okay. You have one other condition at R star is equal to 1, R has to be equal to 0. Okay. Does that condition require that A should be 0? Because if A is equal to 0, you will get back a trivial solution. Okay. Turns out it does not, okay, because this Bessel function goes through 0 at multiple locations. Okay. Just like the sine function goes through 0 at multiple locations, the Bessel function also goes through 0 at multiple locations. Okay. Therefore, the requirement is that J0 of beta has to be equal to 0. Okay. Therefore, beta has to have these discrete values. Okay. And these values once again are tabulated. Okay. You can get values from standard tables, you can get what are the locations at which this goes through 0. This is about 2.40, the next one is about 5.52, the next one is at about 8.65, the next one is at about 11.79 and so on. Okay. So, there is a discrete set of betas, okay. There is a discrete set of betas for which the Bessel function is equal to 0 at R is equal to R star is equal to 1. Therefore, the valid solutions are only those values of beta. Okay. So, therefore, beta is discrete. Beta can be equal to beta 1, beta 2, etc. Okay. There is an infinite set of such solutions. Okay. So, this is the solution of the these are the eigenfunctions and betas are the eigenvalues, okay, the discrete eigenvalues. I told you when you get homogeneous boundary conditions, you get a discrete set of eigenvalues, okay, and a discrete set of eigenfunctions. In the previous case, it was the sine functions and the eigenvalues were n pi. In this case, the eigenvalues are not equally spaced, but you still have a discrete set of eigenvalues. Okay. So, that is the solution for R. What is the solution in time? Okay. Okay. The other equation is equal to minus beta square. Okay. Okay. That would imply that f is equal to e power minus beta square t star. Okay. Once again exponential. Okay. Therefore, the solution for the temperature becomes A, okay, J naught of beta n R star, okay, e power minus beta n square t star. Okay. A combination of the solution for the radial coordinate, okay, with beta having discrete values, so that the boundary condition at R is equal to 1 is satisfied, and the exponential in time. Okay. Of course, any function with one of these discrete beta n's, okay, that is 2.4, okay, 5.52, 8.65, etc. Any one of these satisfies both the boundary conditions. Therefore, it is a valid solution. Okay. Any of these discrete beta n's, beta n, the location at which this Bessel function goes through 0, okay, satisfies the equation. Therefore, the most general solution is one where n is equal to 1 to infinity. Okay. So, that is the most general solution for the temperature field. I have satisfied the boundary conditions in the spatial direction, the two homogeneous boundary conditions at R is equal to 0 and R is equal to 1. How do I get these constants? Okay. These constants a n have to be obtained from the initial condition, because at t star is equal to 0, we know that t star is equal to 1, that is the initial condition. So, from the initial condition we will obtain the constants in this expression using orthogonality relations. Similar to what we had done in the previous lecture, I will continue this and show you how those orthogonality relations are obtained in the next lecture. Okay, I will see you then. Kindly revise what has been done so far, both for the flat geometry where we had sine functions as well as for this particular case, and I will continue this in the next lecture. We will see you then.